In this photo of the east side of Rogers Pass in British Columbia, Canada, there are 5 sheds protecting the Trans-Canada Highway from snow avalanches. The sheds were located where snow avalanches were expected to reach the highway at least once per year. In the storm shortly before the photo was taken, snow avalanches crossed 4 of the 5 sheds. So here's a question. If another slope hazard, such as debris flows, were crossing a mountain pass in multiple places at least once per year, would a national highway be located through the pass? I think not. In this short video, we'll look at why human activities are often located closer to snow avalanches than to other slope hazards. In addition to the point in the previous slide, there are other differences between snow avalanches and other slope hazards. Recognizing these differences help the authors of this book make it more accessible to those who specialize in other slope hazards. The video summarizes some of the key differences. So here are some physical differences. First, the failures that release snow avalanches occur in a bonded granular material within 10 degrees, often within 5 degrees, of its melting point. Second, as we see in this photo of a fracture in a weak layer of buried frost, the samples are too fragile to be transported to the lab. By the way, the only reason the detached slab on the left side of the photo did not slide as an avalanche is that the slope was not steep enough. In other words, the frictional force under the slab was greater than the component of gravity pulling the slab downslope. Snow avalanches can be triggered by explosives, which is an advantage. However, the timing is critical. During and soon after a storm, the window of instability during which explosives are effective can be as short as an hour. This is one reason that explosive triggering systems that can be used 24 hours per day are so effective. This is the Frank Slide in southwestern Alberta, Canada. The deposit has similarities to snow avalanche deposits. In fact, some of the flow models for landslides are also used for snow avalanches. The slide occurred over 100 years ago. 100 or 1,000 years from now, subsurface sampling, or GPR, will be able to identify the extent of the deposit. However, almost all snow avalanches melt in the following summer, so the extent of historical runouts cannot be detected years, decades, or centuries later by subsurface methods. Fortunately for snow avalanche specialists, where snow avalanches run out into forests, the damage to trees can provide a record of past avalanches. This photo shows 6 trees that have been bent by a snow avalanche about 25 years before the photo was taken. Also, an avalanche about 30 years earlier cleared the trees from the area, so this photo is indicative of 2 avalanches in the last 60 or so years. A first estimate of the return period at this location would be 30 years. Let's sum up. In a specific path or track, snow avalanches are much more frequent than most other slope hazards. In many avalanche paths in North America, vegetation damage provides a record of avalanche extent in the preceding 50 to 100 years. Boundaries in vegetation, called trim lines, as well as historical records, combined with statistical techniques, often allow the snow avalanche specialist to confidently draw hazard lines for return periods up to about 100 years. However, for return periods beyond about 300 years, the snow avalanche specialist often has difficulty confidently drawing hazard lines, partly because the deposits melt and subsurface methods do not work. Fortunately, explosive triggering can be quite effective. However, because the failures that release snow avalanches occur within about 10 degrees of the melting point for the ice bonds, the timing can be quite critical. Sometimes the window for intentional triggering is as short as an hour. Because of the lower flow density of snow avalanches, the impact forces are often lower than from other mass movements. This factor, combined with the triggerability of snow avalanches, are 2 of the reasons why human activities are often closer to snow avalanches than to other slope hazards. These are some of the differences between snow avalanches and other slope hazards that we considered when writing the book on planning methods for assessing and mitigating snow avalanche risk.